I'm sure most of you are aware, because hopefully many of you have been to some of the other deep digital machine learning workshops already over the last few weeks. But if you weren't aware, Deep Digital Cornwall is a European Regional Development Fund project here in Cornwall, just at Penryn campus as part of the University of Exeter, but they're mostly here to stimulate the adoption of tech in mining, whether that is through machine learning as these workshops, or big data, or satellite applications in space tech, focusing on the underground. So that could be anything like geology, mining, surveying, geothermal, anything that deals with the underground environment. Deep Digital can be here for you, basically. My name's Alice. I work at the Southwest Centre of Excellence in Satellite Applications. Some of my time is spent on Deep Digital Cornwall. I am the mining theme lead. So at the Southwest Centre of Excellence in Satellite Applications, we have lots of different theme leads, but I deal with the mining and geoscience. So if anyone is watching this presentation thinking, oh, I'd love to do machine learning with some space tech using satellite data, maybe use machine learning to process some Earth observation regional data, then get in touch with me as well. We can help you as well as Deep Digital. So I mentioned the Southwest Regional Centre. The regional centres are basically part of the Satellite Applications Catapult Network. I like to think of them as regional branches, but really we're partnered with the universities quite strongly. So for the Southwest Centre, that's the University of Exeter. We've got people at the Penryn campus. We've got people at the Streatham campus in Devon. We're also partnered with the University of Plymouth, who do mostly marine and cybersecurity and high-tech shipping and autonomous boats and stuff like that, and Falmouth University as well, who do most of the e-health remote healthcare and wellbeing stuff. We've got loads of other associations and projects that we work with, including Spaceport, Aerospace Cornwall, Goonhilly, Camborne School of Mines, TEVI, Marine Eye, and European and UK space agencies who work closely with all of these companies as well. And Deep Digital really should be getting a place on this map because we work very closely with Deep Digital as well. So part of the benefit of engaging with the Southwest Centre is getting to be part of this network, access to this network. I mentioned that I'm the mining theme lead, so you can contact me on this email that's on the screen here. But we also have other themes that we kind of focus on. So if you're watching this and you think perhaps mining isn't the most relevant to you, we cover e-health and e-wellbeing, marine and maritime, and soon we will be recruiting. I think we're in the recruitment process for getting a natural capital. So think more like agri-tech, forestry, fishing, that kind of thing. But at the minute, the manager for the centre is Conrad Gillespie, so you can contact him as well if you don't feel like any of the other themes suit. These are just our focus areas. Within mining, some of the pillars include environmental baseline and monitoring, facilitating social engagement, and creating operational efficiency. But again, if you're thinking of a project or ideas or something you want to do and it doesn't fit into one of those three pillars, don't worry, it doesn't have to. Those are just some examples, really. And then the key offerings of the Southwest Centre, horizon scanning. So we'll keep an eye out for, relevant funding opportunities or events that for people to attend if we think, having gotten to know you and your company, that you might like to learn about an opportunity. That's what we're here for. Connecting stakeholders. So if you're starting a new space tech company, we can connect you with mining companies that you might want to work with, for example, or vice versa. Open space hubs. This is very useful indeed if you are trying to get more into the space tech industry, use satellite applications. We have hot desking space at some of the really cool places, such as, the university for one, very cool, but also the spaceport, Goonhilly, and you can sit amongst the people that are working on the forefront of this tech. So if that sounds useful, get in touch. Thematic specialists, I've already mentioned that. Business support, we do these space tech programs, which are kind of for startups, people develop their ideas. Hopefully I'll have one of those coming up soon. Fostering project consortia, again, if you're known to us and we've engaged with you or you want to do something, we can connect you with the great people to work with, basically, and bid for funding and all kinds of things like that. But another thing that I feel like we offer is that we're basically just satellite experts. If you have any questions about space tech, satellites, applications, things that you can do, what you can't do, what tech is available, then we can be a one-stop shop for all of that, and then offer these main 6 offerings as well. So that was a bit about me, who I am, and the Southwest Centre. But the Southwest Centre is a delivery partner at Deep Digital Cornwall, which is why I am having the honour of hosting this week. And as I mentioned, this is the last week, so welcome to everyone that has come for just this one and any of the episodes before. So today we have Professor Simon Willcock, who's going to be talking about machine learning in ecology. Because this is the last one, all of the listed speakers that you can see above Simon have already been and gone, but all of these have been recorded, as this one is also being recorded. Many of these are on YouTube and probably quite easy to find, but some of them aren't on YouTube. So if you would like to see any of these, get in touch with Deep Digital and they can pass on the recordings or links to the YouTube channel or whatever. So if you have missed any, don't worry about it. So our speaker today, as mentioned, Professor Simon Willcock. He's a professor of sustainability at Bangor University and principal researcher at Rothamsted. So he's going to be talking about machine learning applications, the right thing to do and the wrong thing to do. So I'm going to hand over to you, Simon.
So good morning, everyone. Hopefully you can see my first slide. I am Simon Willcock. I am a professor of sustainability at Bangor. And that basically means that at Bangor, I tend to research the whole environment, whereas at Rothamsted is a agricultural specialist. So in Rothamsted, I tend to focus on agriculture. But to me, they are basically one and the same. And I'll sort of explain why during this talk. So what we're going to talk about today, I'll start with what is an ecosystem service, because that is my area of specialism, and it's just jargon, really. So if I start talking or use any words that don't make any sense, because I'm far too used to the jargon, just yell at me and tell me to stop, but I'll try not to use jargon if I can. And then I'll touch on what machine learning is. I know you've had some of this before, if you've been in the talks before, but we'll touch on it, and I'll flag some things that potentially get hidden. And then later in my talk, we'll discuss why these things shouldn't be hidden. And if someone hides them, potentially they're not doing machine learning very well, for example. So these are useful things to look out for if you're ever going to use machine learning. Then we'll talk about whether machine learning is any good or not, and whether it can save us time and money. And I should lay my cards on the table now. I'm not a machine learning expert. I'm not really tied to machine learning. I am more of a problem solver. So I will use any tool that is appropriate to answer my question, to solve my problem. And that is not always machine learning. Sometimes it is machine learning, and I'll sort of, hopefully in this talk, convince you when machine learning is appropriate and when it's not. Okay. So what are ecosystem services? Well, this is my main area of expertise. And basically, an ecosystem service is any kind of benefit that we get from nature. So the official definition now, I think, is nature's contributions to people. And there is a whole wide range of things that the environment does for us, right? From, carbon sequestration, literally slowing down global warming for us by capturing carbon, to the standard ones that are really easy to imagine, especially in agriculture, growing food. We couldn't grow a food without an environment. But then there are some more abstract ones that are often called cultural ecosystem services. The easiest ones the easiest ones to think about in that group tend to be things like appreciating beauty. So you go on holiday, you pick a nice Airbnb or something, and it's got a really lovely view and you enjoy that, and that's a service of the ecosystem. But also just going for a walk and things like that, so recreation. And these things are often really overlooked. So if we think about agriculture, for one point of view, agriculture as a business, the agriculture is interested in food production, and then they are also interested in some aspects of the environment, mostly because, partly because they're forced to be. There are rules and regulations for controlling the water quality that's flowing off the farm and things like that. So they have to be aware of those kinds of things, but primarily they're interested in food production. And that presents a bit of a friction with, say, the general population, because whilst they need food, something like 70% of England, 70% of England is agriculture. So that's a huge amount of land that then affects effectively, what we do for recreation. So across agricultural land, for example, there are hundreds of thousands of miles of public footpaths. So whilst the farmer, all the on-farm decisions are maybe made pointing towards food production, the farmer is also responsible in many cases for maintaining the footpaths, and potentially there are some things they could do that could make the land better for recreation, better for a walker, for example. And if they did that, or why would they do that? Some do it out of the kindness of their heart, but they're not getting much out of it. But if we can quantify it, then potentially they can get paid for these services. And there are some payment schemes like payment for ecosystem services. The new government one about farming is called ELMS. And ELMS is starting to look into this kind of thing. Can we pay people that manage the land in a way that benefits other people via what we call like public goods? So via recreation or things like that. And there's huge amounts of money in this field. So for example, I think they say the average walk through farmland is worth about £5, which doesn't sound like a lot until you realize how many people walk through farmland. And if you add that up, it's around about 4 billion a year. So, that's a substantial amount of recreational service that farmland is putting on that, farms are not getting payments for because it's currently not captured in any way. So that's what I do. But I've also done research on environmental impact. So I have a project right now actually on the environmental impact of mines in Madagascar and various other aspects of the environment. So I tend to always have that kind of slant. And whilst ecosystem services are a bit strange as a term, they have developed quite good traction with decision makers on the whole. So this actually, all these, the information on this slide comes from decision makers in sub-Saharan Africa, which is one of my areas that I work in quite a lot. And this basically shows that when we spoke to a lot of quite high level decision makers across Africa, that they were already using the ecosystem service approach. One of the reasons for this is, it ties quite well in with business and policy because effectively you can start to monetize it. Not all services can be monetized, but a lot of them can. So it enables people to think about, trade-offs and say, is it worth doing this or that? What's the ultimate loss or gain? But lots of the decision makers do not have enough evidence to make a sufficient decision. So basically, the environment is always horrifically underfunded with research. So, we often don't know. We have no idea what decisions should be made. We often don't have enough data across different time points. But there are certain things that you can do to get a bit more data, like instead of having to get just exactly what value is used where, you can just use ranked information, and any kind of expert really should be able to rank which area is better than which area. But given this huge lack of data, potentially machine learning can step into this gap and say, okay, we don't have much information right now. So with machine learning, can we get much more? And can that help us make decisions? So that sort of brings me on to my reminder about what machine learning is. I won't spend too long on this, I promise. Basically, machine learning isn't that different to any normal identification of a pattern. And I like to say this to a lot of my colleagues who are very scared of using machine learning, when actually it's really not that different. It's just another tool that we've got in the toolbox. In a machine learning process, basically you have data. You tend to split it into two, a testing and a training data set. You then make a model based on the training data set. You look how good it is against the testing data set, and then you've got your model and you roughly know how good it is. This can be an iterative process, so you can tune your model. And if you tune your model, it tends to get better and better and better. But a lot of people actually don't do that, which is ironic. You know, you would want the best model possible. But basically, yeah, machine learning just automates a lot of this, but it's not necessarily anything new in that regard. It just does it potentially a bit faster, potentially a bit quicker. But for example, ecologists have been using what's called stepwise selection. So you can build a general linear model, which isn't machine learning. It's just a normal statistical model. And then you can use stepwise selection to get the best model. That's not that different to machine learning. It's effectively machine learning would do the same thing. It would make a model, and then it would use its iteration process to make the best model that varies on that. So they're very, very similar. So when people think, oh, I need machine learning to do this, actually quite often you could do it using a traditional or a relatively more normal and more standard technique. So it's not always the answer, but hopefully during this talk, you'll see why sometimes it is the answer. So in ecosystem services, we have looked through 308 papers now to see how many of the studies that use machine learning, what they use it for, and what aspects of machine learning are they using, what algorithms and things like that. And broadly, we split the uses of machine learning in the environment into two different groups, predictive and descriptive. So a descriptive use of machine learning, it tends to be unsupervised machine learning. So it tends to be forming it into some kind of group, but where you don't really know what groups you want. So that could be getting a load of data on, say, people and how they're using the environment, and then using clustering, for example, to group these people into sort of different beneficiaries. You know, it might group all the older people together. It might group young men and young women differently if they use the environment in different ways, for example. And we might not know these socioeconomic groups to start with. We might have some ideas, but we might not know. So we can kind of let the machine learning do its thing in an unsupervised way. I would argue that that is one of the better uses of machine learning in this instant. If you don't have an idea of the groups, then using machine learning to sort of think of the groups for you is a brilliant use of machine learning. There's very other options that you've got there. If you've got an idea of the groups, then potentially you've got other choices. And again, if you've got an idea of the groups, machine learning is one of those choices. So you could use supervised machine learning to form the groups that you think are there. The other branch is predictive, which is potentially more useful from a forecasting point of view. So if people are trying to make relationships where they can say, okay, we now understand what's going on. So if we change this part of the system, if we make a land use decision, like mine that area, for example, what's going to happen to the ecosystem services? And that tries to make that relationship a predictive model. So roughly from my field, about 67% of ecosystem service of studies that use machine learning are descriptive, and about 47% are predictive. And I know that that doesn't add up to 100%, and that's because some studies do both. Some of the most common methods are classification regression trees. They tend to be called carts, and clustering algorithms. But by far, you don't really need to, in this talk, to know what they are. Just these are words that may come up a lot. But by far the most common application of machine learning currently in my field is something I think you've already been spoken to about, which is basically remote sensing. So basically using machine learning to better understand satellite data to give us a better idea of what's going on in the environment. That is a really, really good use. And it tells half the story of ecosystem services. Once you understand what's going on the ground with regards to like land cover, that gives you half the story towards land use, which is you just need the other half then, what are the people doing, rather than what is physically there. And that is potentially in my field where machine learning has the biggest sort of gift to give, understanding what the people are doing. And so, as I've mentioned, when you run machine learning, there are various model settings. So I'll give you an example in a couple of slides' time of machine learning that we ran, and it's quite easy to run. But because it's easy to run, that does mean that anybody tends to be able to run it. If you use R, for example, you can actually run a machine learning model in just one line of code. It's not that complicated. But if you don't know what you're doing, potentially you're doing the wrong thing. So of the studies we looked at, all 308 of them, if everyone was doing it brilliantly, on this diagram, you would see all the lines should be on the outside. Unfortunately, often the lines are in the middle, which means it's being done pretty poorly. Some of this doesn't matter. So for science, having freely available data is great. But for a business, you probably don't want all your data to be out there. So, you know, that branch of this diagram is less important to some people in this talk. Others are really quite important. So knowing what the model settings were is really important to being able to get the same answer again. And also saying whether your model settings, if they didn't report the model settings, they haven't done any model tuning. And model tuning is really important because basically there are hyperparameters in the model, and these can really optimize model performance. They can make your model so much better, and they should be varied by the user. A good example of hyperparameters is like when you have a decision tree, or clustering, for example, you can say how many splits in the decision tree there can be, or how many clusters should be formed if you're doing a clustering diagram. And the accuracy of the model that you get out is actually quite dependent on these hyperparameters. So by tweaking them and changing them and tuning them, you can get a much more accurate model. However, we find that the vast majority of people, over 65%, don't bother doing this at all. They just bung it into a machine learning algorithm. They don't seem to understand really what's going on. So they just use the default parameters. The default parameters are often not the best parameters for their data set, and therefore they get an answer that is not wrong. It's just not as accurate as it could be, given exactly the same data and someone that potentially knew what they were doing a bit more. So just sort of a health warning there. You know, if you do decide to use machine learning, then do definitely pay attention to model tuning and make sure that you're getting, you know, the best model you can from the data that you do have. So here is an example of machine learning models using a software called Weka BayesNet. So Weka, I think it came out of New Zealand. It is a really, really easy aspect of machine learning to use. If you've never ever used machine learning and you want to see how easy it can be, just Google Weka, that's W-E-K-A, and download it. It looks pretty much like Windows. It's got, you know, various buttons that you can click. There's no code involved, so it's not as intimidating as other aspects of machine learning. And if you uploaded a data set, so an Excel spreadsheet, in you know, 3 or 4 clicks, you could have run a machine learning model. It's really quite easy to use. So I would recommend, if you want to give it a try or just have a play, try Weka. And what we did with Weka is try and build a machine learning model to estimate where is the most firewood in South Africa. And specifically, we're asking the model to figure out what areas are in the top 25%. Okay, so, you know, so we can protect those areas and we can ensure, you know, those areas are used sustainably. And if we've captured the top 25%, then we know that a huge bulk of firewood is being used sustainably, and we can worry about the lower portion later, because, you know, we've got really limited funds. So it's really useful as a cutoff for, you know, what areas do I need to protect and that kind of thing. We've just asked about the threshold. We haven't asked it to predict the amount of firewood. We've just asked the machine learning to say, are you in the top 25% or are you not? And this is where understanding how machine learning works gets a bit interesting. So in this instance, we're using what's called a Bayesian network. A Bayesian network basically works on probability. So it will say, okay, I think, and it gives you for each district that we've asked it to predict, it gives you a distribution of how certain the model is that it is in the top 25% of firewood sites or not. And that basically means that if you then ask it to give you a summary, it will, using the default parameters, it will then say a site is in the top 25% if it's, you know, if it's the majority, if it's over 50% certain that it's in the top 25%, it will tell you it's in the top 25% if you use the default parameters. 50% certain is not very much. You know, I wouldn't really trust an expert if the expert said to me, okay, yeah, no, I'm going to tell you if it's in the top 25%, but when I'm not sure, I'm just going to toss a coin. And, you know, 50-50, it might be. So, you know, using the default parameters in this instance is not that great, and it doesn't give you a particularly good model. But what you can do is vary that threshold. So rather than saying to the model, okay, if you think it's 50% chance that it's in the top 25%, then, you know, don't categorize it in the top 25%. I want you to be much more sure. Tell me it's in the top 25% when you are 75% certain. Tell me it's in the bottom 25% with the same logic, and anything in between, actually, you know, you can get the model to tell you that you just don't know. And that's really useful. So from a decision maker point of view, it tells you where you need to invest in you know, in collecting more data. It will basically say, okay, we're really certain that this site over here is really important. It's in the top 25%. This one is definitely in the bottom 25%. You don't need to worry about it. We can not protect that one. But these three here, we're not sure about. And actually, when you do that, suddenly the model's making ridiculously accurate decisions, because it is only really declaring a decision when it's quite certain. So in this case, when we made that change, our model was accurate to 96%. So it got 135 out of 140 categories right when it put it in the bottom 25%, and over 91%, 30 out of 33, when it put them in the top 25%. And it actually told us then that 53 it was unsure about. And that was really useful, because then we could go away and say to the, you know, the government of South Africa, in these 53 local municipalities, we're not actually sure how important firewood is. We should look into it further. And that's really useful, because basically this enables decision makers, who are the people that should actually be making the decision, not the modelers who probably don't understand the system, to apply the threshold that is appropriate for them. It then enables the decision maker to use their own judgment. for decisions where uncertainty is potentially higher, because they know the uncertainty is higher. If they just get the answer out, they're just basing it, and they don't understand the logic, then they're just basing the decision on the output. Whereas if they understand the uncertainty around the answer, that's really important too. So for example, given a really limited budget, should we preserve, in my field, or conserve a site that has sort of medium environmental value, but we're quite certain it's medium? Or should we conserve an area that potentially has really high value, but we're not that sure? You know, that the uncertainty then might change the decision you make. And this kind of shows how, I have to move you guys so I can see my own figures. This kind of shows how that the machine learning compares to just other traditional models. So you can actually see in the top row, when the assignment threshold is 50%, so that is the default parameter for this model, the model accuracy was about 64%. So it was only, you know, it wasn't that great. Not that far off half the time, the model was wrong, which isn't that useful for basing a decision, and is actually worse than a lot of the more traditional models. So all the other things listed here, Costanza, Costing Nature, Invest, LPJ Guess, Skulls, they are not machine learning models. They are just traditional sort of process-based models. You know, Costing Nature, for example, which scores quite highly, what's it, 75, 76%. That's really easy to run. You literally just log onto a website, click the area, tell it you want to know about the environment in that area, and it runs a model for you, not a machine learning model, but just a normal model, and it will give you the output. And if that output is giving you it at 75% accuracy, and you know, the fancy machine learning that we applied is only giving you at 64.3% accuracy, why would you use the machine learning? It doesn't make any sense. It was probably harder, slower, probably more expensive, and gave you a worse answer. But you know, we can't make the Costing Nature answer any more accurate. But once we do the model tuning in the machine learning, we can make the machine learning a bit more accurate. So the machine learning after the model tuning, you can see jumps from 64% accuracy to almost 91. So it goes from being one of the worst performing models to one of the best through model tuning. So really, the take-home message that I want to say here is that machine learning, if you're going to use it, it shouldn't be a black box. It should be something that you understand what's being done at each step, and you need to make sure that critical steps like model tuning are not overlooked. And you know, if I was acting as a machine learning consultant, I would just overlook it, because you know, it's much quicker and easier for me to just run it on the default parameters than it is to slowly test, train, and identify exactly what the best hyperparameters are and give you a bit of a better model. So this is coming towards my last slide, and I've given some sort of public health warnings to machine learning, especially in the environment field. But here, I've got a little video of a software that I worked on. It will play in the background while I witter on. This is when machine learning can be really, really useful, if it can actually save us either time or money or both. So this actually is an example of some online software that is using machine learning. So here, what you just saw was me ask or search what models were there, machine learning models, and then ask it to run one of the models in that area. I think I asked it for carbon or something like that, because that's something people are often interested in my field. What the machine learning is doing here is somewhat similar to Google. Effectively, it is taking what you've asked for. You've asked for carbon. It then says, okay, and using artificial intelligence says, right, ask for carbon. How do I figure out what carbon is here? What do I need? and it looks for various models. And then again, just like Google's search algorithm, you know, when you would type in something to Google, Google ranks them. And, you know, all the best results are on the first page of Google. And all the worst ones are buried on like page 9074 or something like that. And that's exactly what happens in this system with models, in effect. So it's looking in this area, it's saying, is there, this is actually Bangor, so it's looking in North Wales, is there a carbon model that's specifically for North Wales in the year that this guy has just asked for? If there is, it will use that one. If not, it might then say, okay, there's not one in North Wales. Is there one in Wales? What about England or Europe? And it knows that potentially a local model is better, or a more resolute model is better. Or if you've asked for 2004, a model of 2003 might be better than a model of 1999. And it knows those kind of things. So it's making these kind of decisions. And as you can see, it's not the quickest on the basis that, you know, it's still thinking. The elephant and the ball is still going around. And I might skip it on a little bit so we don't have to sit here watching it. There you go. It's just about finished now. And you can turn these maps on and on. So the good thing about this software is that it's really transparent. And this is what I should say, what I sort of flagged on previous things. You don't want something that isn't transparent. So it's telling you every layer that it's using, and I can look at every layer. So if I just look at the carbon vegetation, which is being shown now, that's the answer. That's what I asked for. But it also gives me all the inputs that what went into this answer. So it used land cover, for example, and I can see the land cover, that map that it's used, and I could click on things and discover, yeah, I can do a bit of a sanity check. Be like, yes, I know that land cover is in that location. It's not doing something really, really stupid. It also really, really transparently tells you what it did with what bit of data. So you can see here the data flow. And I think potentially the most useful thing about this model is the fact that it can then write the report for you. This is where the time saving really comes in, when people are using machine learning really smartly. If there's a procedure that is not ambiguous at all, it doesn't actually require that much thought, but it does require that much time. So for example, doing the environmental impact assessment, and you have to know certain things, like, is it within 50 meters of a river? You don't need someone to do a GIS map of that and then see if it's within 50 meters of a river and then write a report saying, no, it's not within 50 meters of a river. Artificial intelligence, machine learning can handle all that for you because it's a task that's really easy to automate. As you can see, if I just wind the video back, the report is written in plain English, but this was all written by a computer. So it tells you exactly what things the computer did, in what order. It's got references if you need to go to other places. And it can talk you through absolutely everything to do with this method. So it's a really, there you go, you can see the results and it could write a much bigger discussion. So in this aspect, machine learning can be really, really useful when there's some kind of repeated task that tends to be slightly less ambiguous. And that sort of builds me to my last slide. I think I'm doing okay for time, yeah. That there are some massive pros to machine learning. So they can be really, really easier to build and run. And they have inbuilt uncertainty because they've got that testing training split, which is something that machine learning needs. They often have a much better understanding of their own limitations than, say, a conventional model. So sometimes that's read as a negative. You look at a machine learning model, and because it's telling you how uncertain it is, you start to think that the other model is more certain. But I would always beware of a model that doesn't tell you how uncertain it is, because that means they have no clue how uncertain it is. And a known unknown is much better than an unknown unknown. One of the big pros, as I said at the beginning, of machine learning is using it descriptively rather than predictively, because descriptive machine learning can be used to generate ideas. So you can be like, do you know what? I have no idea what variable is important. Let's just throw loads of variables at it, see which variable it thinks are important, and then we can look into that variable in much more detail. So it can save you a fortune because, you know, rather than having to look into every variable in detail, machine learning has really narrowed the scope of what you have to look into. And that can be used basically to generate your hypotheses for further study. And I think that's a really useful task of it in my field. And it's really, really good for large repeated tasks. So if you've got a large amount of data coming in weekly, like a farmer does in a harvest, for example, then machine learning is great because you don't have time for someone to then sit at that data, give you an update of what you want to do tomorrow. You want that basically to be quick and automated. If you've got a large amount of data, but it only comes in once, then potentially you don't want machine learning. You could give it to a statistician for a week and they could tell you the answer, not using machine learning at all. And that might actually be cheaper. The cons of machine learning, you know, if it is black box, if you don't understand what's going on, or like then there's potential for it to be, you know, less good than it could be. The high parameters, for example, not being tuned. And they can sometimes be harder to interpret. Like machine learning will identify patterns. That doesn't necessarily, you know, correlation and causation are not the same thing. It doesn't necessarily mean that those patterns make sense. They're just there, but they could be caused by an external factor that you don't understand. And because you didn't really dig into the data, the computer did it for you, you might not realize what's going on. So I think that's my last slide. So I'll wrap up there. Take any questions.
Okay, great. Well, we've already got one question in the chat, which was from Laura. She asks, I'm hoping this makes more sense to you than it does me. How would you balance parameter tuning against the problem of overfitting to the data?
Yeah, really good question. Overfitting is, well, it's potentially a huge problem. And what I would then do is just actually, so most people in machine learning will divide their data into two data sets. They will have a training data set and a testing data set. Then you'll get the good people that will also have a data set that they keep back for model tuning. But I would have a fourth data set, and my fourth data set tends to be either years that were not in any of the other three data sets. So if my data set, say, was from the UK, I might do all the training, testing, and tuning on the data I've got between 2000 and 2010, but then I might afterwards validate my model on the data between 2010 and 2015. That tells me, okay, I built the model in this period of time, but how generalizable is it to other periods of time? The same goes for different places. So I might build a model for Tanzania and then test it on Kenya. And that, again, tells me how generalizable the model is. And if the model is generalizable, if that test goes well, then you can be pretty sure that the model is not overfitted.
Nice. Okay, thanks, Simon. And to anyone that's watching, you can add, sorry, I keep jumping around the slides. You can add your questions into the chat. We'll definitely see them if you put them in there. But a couple more questions.
Oh, I've got one actually direct to me, so I better answer that one because it's hidden.
Go on then. Yes.
So what is the recommended accuracy to achieve? It really depends on what you want your decision to be. How important is the decision? So if it's life or death, you want pretty high accuracy, don't you? If it's going to cost you millions as a business, loads. You know, if it's something relatively unimportant, then the accuracy can be much higher. I mean, to me, that's a decision for the decision maker, for the person making the decision. I would just tell them how accurate it is so that they have that in their arsenal to address. So, you know, in the South Africa example, they were thrilled with 90% accuracy. They would have accepted much less, I think.
Fab. Okay, I've got a couple. If you add your questions to the chat, If you send it to everyone, then I'll see it and I can ask Simon. But until then, I've got another question here. Can you combine machine learning with more conventional approaches, combine them?
Yeah, definitely. So you could, for example, use machine learning to make clusters. So when I earlier said that one of the big uses in my field is trying to understand what people are doing. So we could make groups of people using a clustering algorithm for machine learning, but then we could simply correlate, those groups of people with another variable. So are more of these people going to this area just with statistical statistics? That would be perfectly fine. Or you can, as we did in the South Africa example, you could run machine learning alongside a traditional method and just see which gives you the better answer. So there's many ways to combine it. It's just another tool that you should have in the toolbox. It shouldn't be, the only tool you use. It's like doing DIY with only using a hammer. And whilst I'm really good with a hammer, occasionally I do need a screwdriver. It's that kind of thing. You should use the right tool for the right job.
Awesome. And I'll do, unless we get any more in the chat, one last question, which would be, how big should the data be?
Yeah, I would say quite large. Realistically, the advantages with machine learning come when you've got, thousands, tens of thousands, hundreds of thousands of data. So the data's coming in thick and fast, basically, and even better if it's coming in real time. If you've got those boxes are ticks, then machine learning is almost certainly the approach for you. If you've got fewer data and it's coming in much less frequently, then you've got more time to apply statistical statistics and other ways of looking at this. So yeah, that kind of answers. There's no hard cutoff. There's, asking anyone how big is big data. There's no rule, but broadly, that's the kind of thing you should be basing your decision on.
Nice, thank you, Simon. And we've got a question in the chat here from Nicola Wilson, who asks, is Aries still being developed? How do you contribute to it with new ecosystem service models? Any specific gaps that need filling?
Is Aries still being developed? Yes, we're academics. I don't think we've ever finished anything in our lives. We constantly find new problems and keep trying to address them and add to it, and everything can always be improved. So yes, it's still being developed. How do you contribute it with new ecosystem service models? That is its big flaw, right? So Aries is really, really user-friendly. It generally does the modeling for you, it writes the report for you, all those kinds of things. It definitely has a role to play in like future environmental impact assessments, for example. But to get that user friendliness, coding it is really difficult. I mean, it has its own coding language, and as a result, effectively, one of the ways each model talks to each other, to make that happen is very, very difficult. You have to make sure that the output of one model fits with the input to another. You have to make sure that the computer is able to read that, and so it can make its own connections. And that's quite difficult. So effectively, it front ends the difficulty. It gives all the difficulty to the programmers and much less difficulty to the users. So it's quite hard to contribute to. But if you want to, they do training and train you how to code in that way. And then when you can code in that way, if you put it on the Aries cloud, your models will and can be selected. Any specific gaps? There's probably quite a few. I don't know them all well enough to say, but they only really focus on the environment, and the most studied things in the environment are carbon, water, and recreation. So any of the other things are probably gaps.
Some more good. The questions are coming in now. We've got some more, one from David C. So in the foreseeable future, machine learning will not replace traditional modeling totally.
I'm gonna go out on a limb here, and I would say not even in the foreseeable future. I don't think machine learning will ever replace traditional modeling totally. That is kind of like saying eventually the hammer is going to be the only thing in the toolbox. it doesn't really work their way. They all have different pros and cons. So there will be a time and a place for machine learning, and that time and a place will probably get bigger because machine learning is getting better, and it's becoming good at doing more things, but it will never totally replace traditional modeling.
And we've got a few minutes left, so I think why not ask our last question, which comes from Louise Johnson. And it says, when assessing baseline environmental characteristics for an EIA, brackets, you use the example of a 50-meter distance from a river, how do you emphasize the extent of ground truthing fieldwork to the project developer to ensure machine learning picked up any ecological sensitivities not previously known?
Good question. I don't, basically. I don't actually deal with developers, project developers in that way. I am just the academic that makes the tool that can be used. So, for example, we've spoken to Atkins about Aries. They were quite interested in it. They saw really good potential for a tool or something similar to it to, basically free up time. Because if the reports are being written for you, potentially that enables your environmental consultant to do more things like ground truthing. They're charging the same amount, say, and suddenly writing the report takes much less time. So they've got more time to do things like ground truthing and to test the uncertainties and things like that. And they very much should, because that is how things will improve. If we can free up time, that enables you to focus effort elsewhere. And that should be on things like validation and checking and ground truthing and things like that.
Oh, brilliant. Okay, I think that's the end of the questions that we've got. So, well, thank you, Simon, for talking. And anyone that's in the audience that wants to get in touch with Deep Digital to talk about machine learning or obviously anything, the details are on the screen here. I hope that everyone has enjoyed not only this talk from Simon on ecology, but all the other machine learning workshops that have come before. Thanks everyone for coming, and yeah, have a nice Tuesday.